Welcome back everyone. In the last lecture we had seen the relationship between transfer function and state space equations. We saw that if you know the transfer function of a system, then just by looking at the denominator coefficients and the numerator coefficients of the transfer function, you can write down the phase variable state space form for the system. On the other hand, if you have modeled the system using state space equation where you have the matrices A, B, C and D with you, then the transfer function of the system would be given by C Si minus A inverse B plus D. Today we will look into how to solve the state space equation and find out the trajectories, state trajectories of the system and the output trajectory of the system. Before going into the solution of the state space equation or the differential equation x dot equal to x plus bu and the output equation y equal to cx plus du, let us first look into what is known as a state diagram of a system which has state space equations x dot equal to x plus bu and y equal to cx plus du. The state diagram will help you to visualize how the system is connected, and later on when we will be doing controller design, you will know exactly at what point we need to tap in to design the controller or to feedback which signal to the actual system. So, if you have x dot equal to x plus bu and y equal to cx plus du as given here, you can draw the state diagram as follows. So, you can take an integrator, the input of the integrator you can think of it as x dot and the output of the integrator is x a. Then A can be thought of a block of this form, and then you can see that it follows now x dot equal to Ax. Now, we will need Bu. So, x dot equal to Bu. So, this part of the signal, this signal follows x dot equal to Ax plus Bu. Now, we will try to draw y equal to Cx plus du. So, y equal to Cx plus du can be, so d from here you will get du, from here you will get Cx. So, I have to just add them up to get yt. Remember, this is not the actual diagram of block diagram of the system, it is just a block diagrammatic representation which is known as state diagram of the system. Later on we will see that we will tap into some points here to feedback into the system so that we can design the feedback control loop. So, in the PID case, this was your actual plant. When you were designing PID controllers, this was your actual plant. You used to tap in here and then feed this signal back into the system. You had a error block here or a summer here where you used to give reference signal, and then this used to go into the system. Okay. And you will see that in this case we will not be using that, we will be using something called state feedback, and I will come back to this diagram again when we will discuss controller design for this system. Now, let us go ahead and look into the solution of x dot equal to Ax plus Bu. Suppose we first consider a seesaw system which is single state and 0 input. So, remember our state equations are x dot equal to Ax plus Bu, where A is a real matrix n cross n matrix, B is a n cross m, and our output equation was yt equal to Cx plus du, where since I am not writing t anywhere, so let us not write t for y also. So, C was p cross n and D was a p cross m matrix. So, basically there are m number of inputs, there are p number of outputs and there are n number of states. Now, we are simplifying this equation and taking a special case where we are considering that suppose n is equal to 1, that means you have only one state, a single state, and input, there is no input to this case. So, that means your equation boils down to this. So, this is the equation that we are dealing with now, and here n is equal to 1. So, as soon as you see that n is 1, that means this is just a scalar, right, because this is a 1 cross 1 matrix then. So, our state equation and the output equation in this case is x dot equal to Ax and y equal to Cx, where A and C are just scalar quantities. Okay. So, now if I ask you what is the solution of this, now you can see that this is a simple differential equation where we are writing d dt of the variable x is equal to some scalar x of t, and you should know what is the solution of such a differential equation. If you do not remember, let me quickly jog your memory and show you the proof as to how to get to the solution of this. If you multiply both sides by e to the power of minus of at, then you can go ahead and take this right hand side to the left, you can write it in this form, but this on the left hand side whatever quantity is there, that is nothing but d dt of e to the power of minus at xt, and now you can integrate both sides from t naught to t, say where t naught is the initial time, and from here you can go ahead and see the differentiation and integration you can remove, and you have to evaluate the function here at t naught and t. So, finally, the expression that you will get is e to the power of minus at xt equal to e to the power of minus at naught xt naught. So, the final expression will come out to be this. So, this I think most of you should recollect what is the solution of a simple differential equation of this form. So, this is the solution, many of you must already recollect this, and once you know xt, yt is just c of x. So, you can directly write down what your output is. Now, for a seesaw system with single state and 0 input, it is nice, it is a simple expression and it is very easy to solve. However, as soon as we change this to a higher number of states, so which means where your n is no longer equal to 1. So, in that case you can understand that this matrix A now is an n cross n matrix and x is an n cross 1 vector. So, you have n number of state variables and the state vector is of dimension n cross 1 now. Now, the claim is that like in the seesaw single state case, we had e to the power of a t minus t naught x t naught. Here also it will look like e to the power of capital A t minus t naught x t naught. Now, you have to be very careful here. Notice that this quantity is just a 1 cross 1 scalar. This is because this was 1 cross 1. Now, here this is n cross n because I have not considered n equal to 1 here. So, this one must be n cross n because on the left hand side I have to get an n cross 1 vector. So, this matrix here, so this is a matrix e to the power of a t minus t naught is no longer a scalar, it is a matrix and the dimension of this matrix is n cross n. So, of course, the question would be how do we find out this? We will come to that soon. Now, if once you know, once I have claimed that this is the solution, if I am assuming that I can prove this, which I will be able to because I have already claimed this, so I know what the solution is, that is why I am telling you that this is the solution. So, I will prove it of course, but once you know this solution, you can see that the output can directly be found out because yt will be equal to c into xt. What is x? E to the power of a t minus t naught x of t naught. So, once you know the state response, this is called state response. Once you know the state response, then or the state trajectory. So, there are different terminologies used, you can call it state response, you can call it state trajectory. Once you know that, it is easy to find out the output because output is just c into x in this case. Okay. Of course, I have not considered the input yet, I am just considering 0 input now. So, let us try to see whether this is exactly a solution. So, what we will do is, so again remember what we are claiming is that if you have x dot equal to ax, a differential equation. So, how many differential equations are here? Here is a thought experiment, you think about it. Okay, how many differential equations have I written here? Okay, remember this is n cross n, this is n cross 1 and this is n cross 1. So, how many differential equation do you have? You can pause the video here and think about it. Okay, so there are n number of differential equations because there are n equations that you will get. So, you have n differential equations and we are asking what is the solution of this, and you can also see that this is a coupled differential equation, right? What do you mean by couple? So, for example, d dt of x1 x2 is equal to say 2 1 1 1 x1 x2. So, the differential equations here are d dt of x1 is equal to 2 times of x1 plus x2 and d dt of x2 here is equal to x1 plus x2. You see the solution for this depends on this and the solution for this depends on this. So, these are coupled in that sense. Okay. So, now we will try to see that the claim that I have made, that this is the state response, is it valid or not, and we can show that by simply putting on the left hand side this expression and showing that it is equal to the right hand side, and that is what I am going to do now. So, on the left hand side we have x dot can be replaced as d dt of x of t. So, x of t is this, I have written this. Now, here I will use a series where this term here can be written down in a series. So, you remember e to the power of a t is where a is a scalar, is a series of this form, a 1 plus a t plus a square t square by factorial 2 and so on. Similarly, it can be shown that e to the power of capital A t is a matrix of the form I plus capital A t plus a square t square by factorial 2 and dot dot dot. So, this is an n cross n matrix, whereas this was 1 cross 1 case. Okay. So, e to the power a t, the matrix exponential, this is a matrix exponential because it is a matrix in the power here. So, it is a matrix exponential, the matrix exponential can be written down in this infinite series. So, I am writing the inner part here in this infinite series. So, we actually are doing this. Okay. See, since here t is t minus t naught, you can see that t has been replaced by t minus t naught. Now, once we have that, I can multiply this x naught with each of this term, and then I can open up the differentiation. And that is what has been done here. So, I times of x t naught, a times a t minus t naught d dt of this a t minus t naught x t naught. Again, you can see that this term is 1 cross 1, this is n cross n, and this is n cross 1. So, that is why I am writing it like this. So, this is n cross n, this is n cross 1. So, you can rewrite this expression like this. Now, the question is, what is d dt of I x t naught? So, d dt of a matrix, differentiation of a matrix is differentiation of each element in that matrix. So, you can see that this is a constant matrix. So, therefore, this part will go to 0. Now, comes this part. What will be the d dt of this expression? The d dt of this expression would be, so what is d dt of a t minus t naught x of t naught, and you can see that this can be written as d dt of a x of t naught t plus or minus t naught a x of t naught. Now, this part is a constant. So, d dt of that part will go to 0, whereas the d dt of this part will be equal to a x of t naught, and that is what is being written here. Okay. Similarly, you can look at the next term. Let us look at the next term. So, a square remains as it is. So, this part will be 2 t minus t naught. So, the differentiation of this part will be 2 t minus t naught, and this is what you will get, 2 t minus t naught by factorial 2 and x of t naught. Similarly, for the a cube part as well. So, this 2 and this 2 will cancel out. So, you can see that in this expression, you can see this is n cross n, this is n cross n. So, from the left I can actually go ahead and take a common, and I can write down this expression in this form. You can x t naught I am taking to the right and a I am taking to the left. So, this is again an n cross n matrix, this is an n cross 1 vector, and this entire thing is n cross n. Okay. Now, the middle part here is nothing but the exponent series again, right. So, I can write down e to the power of a t minus t naught, but you can see that what is this? This part is nothing but x of t, because that is how we had defined. So, you can see the left hand side has become equal to the right hand side. Therefore, this is indeed a solution of x dot equal to a x. Now, we take the case when we have some inputs. So, here we are no longer considered 0 input case, we have considered that we have some input and we also have some initial conditions. Now, the claim is that the solution will look something like this, x t will be equal to this part plus this part. Notice that this part was the 0 input state response. So, this part was the expression when we took input to be 0. So, this is nothing but the 0 input state response. Okay. So, the response of the state when input is 0, okay, and the 0 state response, or when the initial condition is 0, that response is given by this part, Remember, output response was divided into two parts, 0 input response and 0 state response. Similarly, state response can also be divided up into two parts, one when you have no input and the other when you have no initial conditions. Okay. So, these are the two parts, and now we will show that this term is the solution of this. Now, notice carefully what is it looking like. This part we already know what to do about this, and on this part is the one which is coming due to the input. So, again similar to the previous case, for the 0 input case, what we will do is we will substitute on the left hand side this expression, the claim that xt is equal to this expression, and let us see what happens. So, when I substitute that, you can see these are the two terms that I will get, right. If I take the differentiation and I distribute it over, so these are what we will get. This part we have already computed, right. We already know what this part would be. If you remember, this part was a of x of t, right, because this is exactly what we did just now. Now, only thing is that we have to look into this part and see what do we get. So, ddt of this part will be, now to evaluate this part we will use something called the Leibniz rule. You can look it up in any calculus book, you will always get it. So, the Leibniz rule says this. So, ddt of integration of at bt f of t t tau d tau can be written down in this form. Now, let us see how does this expression fit in to this Leibniz theorem. So, you can see that here at is t naught, bt is t, and the function here is this expression. So, f of t bt, so f of t, so tau will be replaced by bt, bt is t here. So, tau is replaced by t in this case. So, when tau is replaced by t, we get this will be t, and then we have b of ut, then ddt of bt, bt was t. So, ddt of t minus f t a t. Now, a t is t naught here. So, tau will be replaced by t naught, b u t naught, ddt of a t, but a t is t naught here. So, we have ddt of t naught plus integration from t naught to t, partial fraction with respect to t of the function, again e to the power of a t minus tau b u tau d tau. And now, notice that it is easy to notice that this part will go to 0, right, because this part is going to 0, because that is a constant. So, we will be left with e to the power of a t minus t b u t plus integration of t naught to t, partial derivative of e to the power of a t minus tau b u tau d tau. Now, what is this expression? Now, what is e to the power of 0? Again remember, this is an n cross n matrix. So, when you are writing e to the power of 0, this is also an n cross n matrix. So, basically the matrix here is A now. So, if I write down it in the form, what was the form? I plus a t plus a square t square by factorial to dot dot dot. This was the form. Now, in this case you have taken t to be 0, you can write it down as a into 0. So, that is why you will be only left with the identity matrix now. So, e to the power of 0 will be the identity matrix, and let us look at this term. Now, this term again, what is this term? E to the power of a t minus tau b u tau. Now, this term again we can write it down again. We have already done this part in the previous case. We can write this down again in this form. And then if we differentiate, we will be left with a, and then we will have a square t minus tau, then we will have a cube t minus tau whole square by factorial 2, and so on, and from here on the left I can take a as common, and I will be again left with the same term. The derivation is exactly similar to the derivation that we did when we showed that x dot equal to a x, that 0 input case. Okay, I am not rewriting that again, you can go ahead and look at that. Now, notice that this will be the expression. Now, a I can take out, e to the power 0 has been replaced by identity matrix into b is b, and then a I am taking out. Now, you can see that this is the expression that I am left with. So, this is the expression that I am left with. I will use this expression in this term. So, this part I am replacing with this, and now what am I getting? You can see this is the expression that I had already seen we will be coming out when I differentiate this, and so and from this part I am getting this part of the expression. So, you can take this and this together, take A as common, and this is what I can rewrite it with. But notice that this is nothing but this expression, right. So, I can replace it with x. So, you can see that I have proved that x dot equal to Ax plus Bu. So, which means that this is indeed a solution of this state equation. And now, once you have the solution of the state equation, the state response, which was this, finding out what output is very easy, because it is Cx plus du. So, C multiplied by the x expression, the state expression that you have got, plus d into u, and this is called the output response of the system. So, the complete response of the system is given by this. So, if I ask you, see, this is the response of the system, right. So, I know that the response of the system can be divided up into 0 input response and 0 state response. Now, I would urge you to think from your own as to which part of this expression corresponds to the 0 input response and which part of the expression corresponds to the 0 state response. You think about it on your own. Okay. Remember the definition and try to implement, you will be easily able to figure out which part is corresponding to what. Now, let us try to solve this example where you are given a system x dot equal to Ax plus Bu, y equal to Cx, and you are asked to find out the step response of the system if initial conditions are 1 1. Okay. We will try to solve this question now, and this question can be solved in several ways actually. You can have several ways of solving this question, and we will solve it by one method today, and in the next lecture we will take up another method. So, let us look at this expression and try to find out the solution of this. So, first, whenever you have this question, you have to understand what is the question. The question is, you have to find out the step response of the system if initial condition is 1 1. So, you know what the input is. So, what is the input here? The input here ut is nothing but u step of t. This is the input. So, you know that us is nothing but 1 by s. Okay. So, now let us try to find out the solution for this. So, this method 1 is based on the Laplace transform. Remember, if you remember in the previous lecture we had seen, if you have x dot equal to Ax plus Bu and you take Laplace both sides, then the expression can be written in this form: s of xs minus x of 0 is equal to A of xs plus B of us. So, here you can again write down Si minus A xs is equal to x of 0 plus B of us, and from here you can write down xs is nothing but Si minus A inverse x naught plus B of, or Si minus A inverse B of us. So, once you know this, you can see that Ys is nothing but, from here you know that Yt's expression is nothing but Cx plus du. So, if you take a Laplace here, this is nothing but Ys equal to Cxs plus d of us. So, xs you can replace from here, and this is the expression that you will end up with. I have already done this derivation earlier, I am just showing you to recap things. Okay. So, this is the expression that you get. So, from this expression you can see that I can find out Ys just by calculating this part, and once I have Ys, I just have to do a Laplace inverse of Ys, that will give me the step response, right. So, that is what we will do here. So, let us go ahead. So, first of all we will try to find out Si minus A, because we will have to find out Si minus A inverse. So, we will try to find out Si minus A first. So, I means a 2 cross 2 matrix here, identity matrix here, which is 1 0 0 1, you can see that, and then Si minus A, it is a simple matrix subtraction which will give you this expression, and then when you go for Si minus A inverse, this will be the expression. So, what is the inverse of A, B, C, D, this type of a matrix? If you remember, the inverse is A, B minus D, C, B, C, B, A minus C minus D. So, this is the inverse of a 2 cross 2 matrix, you can go ahead and multiply, you will get an identity matrix there. So, I have used the same thing, you can see I have just swapped this, of course, it is not visible here the swap because both are the same elements, and then the signs have changed here. So, this is the expression that you get. So, once you have Si minus A inverse, you can see I can write down s plus 2 divided by this is nothing but s plus 2 whole square, you can see that, and I can rewrite it in this form. So, this is the Si minus A inverse matrix, and so now if I plug in the value C from here, B from here, and Si minus A inverse that we have just now computed, x0 was given to be 1 1, and once you find this, it is just a simple multiplication. Of course, us is 1 by s here because u of t was equal to u step. So, u of s is equal to 1 by s, and once you do this multiplication, you will get something like this. So, here again d is 0, remember. So, once you multiply, this is what you get, and final expression will be this. Now, if you remember, since I have already told y of t can be found out by Laplace inverse of ys. So, I am writing down ys here in the partial fraction form as given here. So, yt will be nothing but 3.5 minus 1.5 e to the power of minus 2t for t greater than equal to 0. So, this is the complete response of the system. So, by this method you can easily find out the response of the system, and you can notice that this part is the transfer function, remember. So, you remember, right, output is equal to transfer function multiplied by input. So, once you have the transfer function, you can get the 0 state response directly. Okay. So, if you would have calculated this part, you would have got the 0 state response, right, because the initial condition in that case would have been 0. So, you can think of all this now and try to figure out which part will be again 0 input response, which part will be 0 state response. In the next class, we look into another way of finding out the same thing, solving the state equations. We will take the same example again, and we will see how to find out what is known as matrix exponentials. Thank you.